Hello, welcome to this video where we're going to discuss subsequences of sequences. So we'll go through a definition or two, then we'll prove some basic properties of subsequences, and we'll cover the Bolzano-Weierstrass theorem in a different video. Okay, so what is a subsequence? Well, you start off with a sequence, so suppose Sn is a sequence. A subsequence of Sn is another sequence that you form from the terms of Sn. And so here's the key. You select some or maybe all of those terms, and you have to preserve the order of your original sequence. So if you start off with like your sequence Sn being S1, S2, S3, I could form a subsequence SNK, and I can decide what is the first term of my subsequence. I don't know, maybe it's 17, so it'll be S17. Now what's the next term? I can't pick S2, right, because I have to preserve the order, but I could choose any term after 17. So maybe the next term is S18. And then maybe the next term is S100. And the next term is S2027, right? So one thing that students sometimes believe is that when you have a subsequence, you have to have a pattern to how you choose the terms. Like, oh, I have to choose S1, then S3, then S5, and S7. Or I have to, there doesn't have to be a formula on how you get NK. Okay, so a subsequence is just any sequence of the form TK where for each K there is a positive integer n sub K such that TK is equal to SNK and your terms are increasing. Or the index is increasing, not the terms, sorry. Okay? So if we look at the example I have here, I'm going to use a different color. T1 would be S17. T2 would be whatever S18 is. T3 would be whatever S100 is, right? And so N1 would be 17. N2 would be 18. N3 would be 100. So the N sub K just tells you which term you're using, okay? Let's just work through an example here. List some possible subsequences of this sequence here. So this is -1 to the n times n squared. So this is the original sequence, -1, 4, -9. So you got n squared, and then you're alternating plus and minus. And I just wrote down 3 here. So I could choose this to be my first term of my subsequence, -9 to be the second term of my subsequence, right? I could choose every other term and create a subsequence. That's great. What I can't do is choose, I can't repeat a term because 4 doesn't happen anywhere here. So once I choose 4, then I have to look at increasing index. So I'm not saying it right. What I want to say is these inequalities are strict. So you can't choose S sub 2 twice. Once you choose S sub 2, you have to move on and choose a term that's further down your sequence. If I had a sequence, I don't know why my pen is doing that, but say my sequence is 1, 1, 1, 2, 2, 3, 1, 7, 6, 9. So it's just some random sequence. Now I could have, this is my first one. This one as my second one. This one as my third one. This one as my fourth one, right? So you can have, it's not like your subsequences have to be monotonic. They don't have to be monotonic, but what has to happen is you cannot repeat a term. So once you pick, say, the nth term, then for your subsequence, the next term in your subsequence has to have a higher index than the previous one. Okay. Hopefully that's clear, but I didn't do a good job of explaining that. Basically, if you start off with this example here, you can't have this as a subsequence. But you could have just, 16, and then you could just choose random. There doesn't have to be a pattern to how you choose the terms of your subsequence. Okay. Now let me give a different definition. This is a definition of a subsequential limit. So the key here is subsequential limit. So you have a sequence and Sn, and maybe the sequence doesn't converge, but perhaps it has a subsequence that converges. Well, the limit of a subsequence of Sn is called a subsequential limit of Sn. So let T be a real number. Then T is a subsequential limit of Sn if there exists a subsequence, Snk, that converges to it. And then usually we denote the set of subsequential limits by S. And the reason why we care about the set of subsequential limits is because the limits of the subsequences of your sequence tell you about the behavior of the original sequence. So you can think, imagine you're analyzing data and you have all these data points, and looking at all of the data might not give you any information, but maybe if you look at just a subset of the data, you see a trend, right? That's kind of the idea when you're looking at subsequential limits. And we'll be able to prove things like, we know that every sequence every bounded sequence has a lim sup and a lim inf. Well, it turns out that there will be a subsequence that converges to the lim sup, and there will be a subsequence that converges to the lim inf, right? It turns out that your sequence converges to a real number if and only if its set of subsequential limits is a singleton. So, looking at the subsequential limits of a sequence gives us information about the original sequence. And let's practice computing the set of subsequential limits for the following sequences. So let's look at this example here. This one we kind of already started looking at it. Now, if you think about all the possible subsequences, do any of the subsequences converge to a real number? And the answer is going to be no. And the reason why we can say that is because any subsequence is going to be unbounded. And we know that convergent sequences are bounded. So, for number one, we'll say our set of subsequential limits is an empty set. I don't know what's going on here. Any subsequence will be unbounded, and convergent sequences must be bounded. So no subsequence is convergent. But we can say that we could have a subsequence that diverges to minus infinity, and we can have a subsequence that diverges to plus infinity, right? So that's definitely the case. What about number 2? So when I look at number 2, I wrote down the values. So these terms oscillate between 0 and plus and minus root 3 over 2. So any subsequence that converges will converge either to 0 or, right, like we could pick 0, 0, right? We could pick the ones that are converging to 0. You also have a subsequence that's converging to root 3 over 2. And the next would be root 3 over 2, root 3 over 2, and then minus root 3 over 2. So our set of subsequential limits would be 0, root 3 over 2, and then negative root 3 over 2. Okay? And then for the third one here, suppose you have an enumeration of Q. So if you have done the extra credit homework, you know that Q is countable. So that means that you can, theoretically, you could list all of the numbers in Q as a sequence. You can't do that for R because R is not countable, R is uncountable. But Q is countable, so there exists a bijection between the set of natural numbers and Q. And that bijection gives you an enumeration of Q. Here's the key. We're thinking about subsequences of Q, and we're thinking about limits of subsequences of Q. And because Q is dense in R, every real number is going to be the limit of a sequence of rational numbers, right? So if you take all the rational numbers and you write them in a sequence, you'll have a subsequence that converges to, for any real number, you'll have a subsequence of rationals that converges to it. Okay. So now let's look at this question here. Under what conditions is T a subsequential limit? If you had a hard time believing me, right, because I kind of didn't give a proof for any of these. I just said, let me think about what subsequences could converge to. And that's not a concrete proof. But the easiest would be to prove that for number 2, the set of subsequential limits is 0, root 3 over 2, and negative root 3 over 2. And then here's just a sketch of the proof. Zero plus and minus root 3 over 2. I don't know what's wrong with it. I think maybe I need a new, sorry. Maybe I need a new top because so let's see here. And then plus or minus root 3 over 2. For Sn equals, what was it, sine of n pi over 3. So this will be the goal. And remember, how do we prove S is equal to this set? How do we prove two sets are equal? First, we would say, I'm so sorry, give me a minute here. Let me just rewrite this because Here's how we would do this. So hypothesis, Sn, and this is for each n. Sn is equal to sine of n pi over 3. S is equal to the set of subsequential limits of Sn. And then my claim is S is equal to 0, root 3 over 2, and minus root 3 over 2. And then for the proof, first, 0 belongs to S because, and then I would say, let Snk equal 0, 0, 0, right? Has a sequence going to 0. So each nk could be equal to 3k. So if n is a multiple of 3, then Sn is going to be 0. So I would want to take S3, S6, S9, right, S12, and that'll give me my subsequence that converges to 0. Okay, and then similarly, root 3 over 2 and negative root 3 over 2 belong to S. So now, on the other hand, we need to show that everything in S is one of these three. And the way I would show that every subsequential limit belongs to here, belongs to this set, is I would say, perhaps do a proof by contradiction. Say X belongs to R, but it's not 0 and it's not plus or minus root 3 over 2. We want to show there does not exist Snk converging to X. Okay, so now here's 0, and here's root 3 over 2, and here's minus root 3 over 2. And now the terms start off, where do we say the terms start off at, like, so like this is S1, and it's also S2, and then here's S3, and then here's S4, and S5, and S6, and S7, and S8, and S9, and S10, S11, S12, S13, right? So we're just kind of hopping back and forth between these three. So I would say fix X. Suppose you have a point X, and it's not one of these three numbers. Maybe X is over here, right? Then I can find an epsilon ball centered at X, and this epsilon ball will have no elements of Sn. So if I have an epsilon ball centered at X, right, X minus epsilon to X plus epsilon, and it contains no elements of Sn, then no subsequence is here, right? And if you have a subsequence converging to X, that means all but finitely many terms of your subsequence are supposed to be in this interval. And if I can find an interval where there are no terms, that means that no subsequence can converge there. Yeah. So that would be the argument. And it's similar to the argument, I think, from one of the homework problems where you show -1 to the n doesn't converge. Okay, so that kind of is a really good segue to this theorem here. Because this theorem is saying under what conditions will a real number be a subsequential limit of a sequence. And here's the key right here. We're saying, so the idea is that fix a real number, there's a subsequence converging to it if and only if for every epsilon greater than 0, this set is infinite, right? If and only if this interval is infinite. Now, if your sequence is unbounded above, then it'll have a subsequence that diverges to plus infinity. And if your sequence is unbounded below, right, so that means it doesn't have a lower bound, then there will be some subsequence that diverges to minus infinity. And then this is really special. In each case, the subsequence can be taken to be monotonic. Okay, so let's kind of run through why this would be true. We'll start off with this first one here. So we're saying if you have a real number, there's a subsequence converging to it, i.e. t belongs to S if and only if for every epsilon greater than 0, S minus epsilon to S plus epsilon, or T, sorry, contains infinitely many elements of the sequence. So let's just write this down here. So for hypothesis, we're going to say Sn is a sequence of real numbers. And then let's say T is real, and S is the set of subsequential limits of Sn. So the claim, T belongs to S if and only if for every epsilon greater than 0, this set is infinite. So for every epsilon greater than 0, the set of n such that the distance between Sn and T is less than epsilon is infinite. Okay, so for the proof, we have two directions that we need to show. So let's do, suppose T is an S and fix epsilon will show that this set is infinite. Well, if T belongs to S, then that means that there's a subsequence converging to T. And so if we have a subsequence converging to T, that means for any epsilon greater than 0, all but finitely many of the terms of the subsequence are within epsilon units of T. So let me say that again. Snk converges to T if and only if for every epsilon greater than 0, all but finitely many terms of the subsequence Snk belong to t minus epsilon to t plus epsilon, that interval. So let's write that down. S and K such that S and K converges to T. So there exists for this epsilon, there exists an n such that nk bigger than n implies the distance between S and K and T is less than epsilon. So that means the set of nk such that the set of nk bigger than n is a subset of the set of n and n such that the distance of S between Sn and T is less than epsilon. This set is here. This set is infinite. So if this set has an infinite subset, it has to be infinite. Okay. Does everybody get that? So we have our sequence S1, S2, and then we have some subsequence SN1, SN2. There's some index after which all of the terms of your subsequence are in this interval. So that means you have to have infinitely many indices where this inequality is satisfied, okay? So if T is a subsequential limit, then this set is infinite. And now let's prove the other way. Suppose for every epsilon greater than 0, this set is infinite. We have to show that there's a subsequence converging to T. And further, we need to show that the subsequence can be made to be monotonic. Okay? So let's see here. On the other hand, suppose that for every epsilon greater than 0, this set is infinite. We want to show there exists S and K monotonic such that S and K converges to T. Okay, so how are we going to do that? I'm going to, let's see here. Let's just see if we kind of believe it. So here's T, and we're saying for every epsilon, there are infinitely many indices of your sequence in here. So say epsilon equals 1. That means we're looking at T minus 1 to T plus 1. There are infinitely many terms in here. Okay? So the set of So since there are infinitely many terms in this interval, there's got to be one term, and let's pick it. So pick Sn such that the distance between Sn and t is less than 1. Okay, call that one S1. So we have our sequence here, S1, S2, S3. And one of these, well, infinitely many of these are in here. So we're saying just pick one of them. Pick one of them. Okay. So call that one, it's going to be our first one, so let's call it S sub N1. So I'm going to say maybe it's right here. Maybe that one is S sub N1. Now, remember for every epsilon, the interval t minus epsilon to t plus epsilon has infinitely many indices in your sequence. So choose an epsilon that's small enough to not include Sn1, right? So we're going to say let epsilon, so this was let epsilon equal 1. That got us Sn1. Now we're going to say let epsilon equal, and I'm going to say the minimum of 1/2 and the distance between Sn1 and t. So that guarantees that my next term, Sn2, because remember I'm building a subsequence that converges to t, that guarantees that Sn2 is going to be getting closer to t, right? Because I'm going to say then the set of n, and now watch this. Because we have Sn1 somewhere in this list, so somewhere in this list is Sn1, right? And then after that will be Sn1 plus 1, Sn1 plus 2, and it'll go on forever, right? Now, if I just look at this set here, infinitely many of them have to be in my new interval. Why? Because there are only finitely many numbers less than or terms before Sn1. And if there are infinitely many terms in this interval, and there are only finitely many terms here, then there have to be infinitely many terms from here in this interval. So I'm going to say the set of n bigger than n1 such that Sn, the distance between Sn and t, is less than epsilon, this new epsilon. This is an infinite set. So choose one of these and call it Sn2. So then we say, okay, now I have another one. Maybe this is Sn2, right? And then I'm going to repeat this, and I'm going to say, okay, well, now let epsilon equal the minimum of 1/3 and the distance between Sn2 and t, right? The reason why I have to do the minimum and I'm doing this 1/n is because I don't want to keep picking terms like S1 is here, S2 is here, S3 is here. I want to make sure that my SNs are getting close to t, yeah? So I'm kind of forcing that by having my epsilon be no bigger than 1/n, okay? So you keep this up, you iterate this, and iterate this process to build a sequence, a subsequence, Snk, such that the distance between Snk and t is less than 1/k, right? this implies my SNK is going to converge to T. Now, so what we've said is if I know that for every epsilon, I have infinitely many terms in my sequence in that interval, then I can kind of construct a sequence, a subsequence that converges to T. The thing that I didn't do is make sure this monotonic. And you can go back and adjust what we did to ensure it's monotonic. Let me show you how to do that. So when I pick my SN1, okay, now I have my new epsilon, right? Remember we said, okay, now let epsilon be the minimum of 1/2 and the distance between T and SN1. Well, don't use T minus epsilon to T plus epsilon as your interval. Just use this. So if I just use the left side, then my SN2 has to belong in here, right? I'm using the left side, so that way I would build a sequence that's monotonic. Does that make sense? So to get my sequence to be monotonic, let me use a green here. What I would say is instead of saying that this set is infinite, I would say this set where T minus epsilon to T, right? Set of n bigger than n1 such that this set, let me write it here. The set of n bigger than n1 such that Sn is in between T and T minus epsilon. This set is infinite. It's still infinite. And so choose that. And how do I know it's infinite? Well, could this set be finite? If this set is finite, so I know that this whole set has infinitely many of the terms. So either this has infinitely many or this has infinitely many, right? And now, if this has finitely many, then this set now has infinitely many. And so then I would say, okay, well now you can build your sequence using this side here. Because if this side has infinitely many, now when I go to restrict, I'll still have to have infinitely many in here because I'm always dealing with that. The interval has to be centered at T. So I can't have it where this has infinitely many and this side has finitely many. I can't have that. So I would have infinitely many every time that I'm kind of restricting my interval. Okay. So that kind of walks you through how we would prove the first statement here. So we're basically able to say elements of S, i.e. subsequential limits, are those points, those real numbers where every epsilon neighborhood, every epsilon interval contains infinitely many of the terms of your sequence. Excuse me. And then we say, well, what if you're talking about a sequence that is not bounded above? How do you know you have a subsequence that diverges to plus infinity? And right, if you're not bounded above, we can kind of walk through this very easily. Let's see here. If you're not bounded above, so hypothesis Sn not bounded above, and then the claim, there exists Snk diverging to plus infinity. Then the proof, so since Sn is not bounded above, that means for every n and n, there exists m, we'll call it m sub n, such that I should have used a different one here. So I'm going to do it here. Such that little n bigger than m sub n implies Sn is bigger than n. So in particular, so there exists an m. So for n equals 1, there exists an m1 such that n bigger than m1 implies Sn is bigger than 1. Okay? So use that m1 for your first term of your subsequence. And then you repeat for n equals 2, right? Pick a term past this so that your Sn is bigger than 2. So pick a term past m1, right? There exists m2 greater than m1 such that blah, blah, blah. And so in the same way, you're kind of building your sequence. You can make it so that your terms are increasing. And you say the Sn is bigger than the max of S1 and 2, right? So to make sure that you're diverging to plus infinity and you're also monotonically increasing. Okay, and then monotonically decreasing is very similar. Okay, so the last thing I wanted to do was talk about this, I think the last thing. Yeah, or no. Corollary. For any t, there exists a sequence in Q converging to t. In other words, every real number is the limit of a sequence of rational numbers. So this is going to follows directly from the density of Q and R. Because what we're saying is in between any two real numbers, you have a rational number, right? So that means in between any two, you have to have infinitely many rational numbers, because if you only had finitely many, then you'd have a contradiction because you have an interval in between any two of those rational numbers, and that one has to have a rational number, right? So you can't have just finitely many rationals, because if you did, then you would have intervals where there are no rational numbers. Contradicts the density of Q and R. Therefore, every interval has infinitely many rational numbers. Therefore, every real number satisfies this right here, right? If you're doing an enumeration of Q, there will be infinitely many elements of Q in any epsilon neighborhood of T, okay? And now this last one here, if a sequence converges, then every subsequence converges to the same limit. That's pretty basic. So you have your S1, S2, S3. It's converging. Say the Sn is going to S, okay? Then if you have a subsequence Snk, fix epsilon greater than 0. There's some point here, Sn, where all the terms are going to be within epsilon of S, right? All the terms after Sn will be within epsilon units of S. We'll notice that Nk, or N sub N, right, has to be bigger than or equal to big N. So whatever your subsequence is, after some point, the remainder of its terms are going to be within epsilon units of S, simply because these terms are coming from your original sequence, okay? And I know I'm being a little sloppy in explaining this, but don't worry, the Ross has a formal proof. So I'm just kind of giving you an idea of why it would be true. And then the last thing here is this Bolzano-Weierstrass theorem. This is huge. Every bounded sequence has a convergent subsequence. And again, this is going to come essentially from using the completeness axiom. Yes, to prove this. Watch the next video for the proof of Bolzano-Weierstrass theorem. Yeah. And let me know if you have any questions.